My name is Mike McLaughlin, and it's my pleasure to be moderating this session with so distinguished panel. Let me first introduce our panel, if I may. We're going to be hearing in a few minutes from Eric Peterson, a vice president in our Medford, New Jersey office. Eric has got a degree in civil engineering and has been with SCS for 35 years. Mark Huber will be speaking to us about alternative energy in a little bit. Mark is a vice president based in our Madison, Wisconsin office, and Mark has been with the firm for 26 years. And I'm the old guy. I've been with the firm, I started as a summer intern in 1973 and worked on my first landfill redevelopment project in 1976. And if you add up all the experience this panel has, we've been with SCS engineers for more than 100 years, which I think is pretty interesting. SCS Engineers was founded in 1970, and our very first project was a landfill gas migration problem from the Palos Verdes landfill out in Southern California. That was about a half a mile north of where golfer Tiger Woods went off Hawthorne Boulevard here in the last few days in his tragic accident. So that which is old is new again. The concept of redeveloping landfills really began in Southern California, I think. Back in those heady 1970 days, real estate was just so expensive and is still so expensive there that that was the first place where people had the temerity, if you will, to redevelop a landfill. And a landfill can be redeveloped for just about anything you can imagine. I've got a little potpourri of land uses on this slide, but there are scores and scores of other examples out there, everything from residential to commercial, to a lot of recreation activities and so forth. I've said that landfill redevelopment can be smart growth. And I think that's because landfills are often near great highway access. That's one reason why the landfill's there. There's existing infrastructure there. They've got all the kinds of utilities and so forth are often been built out to landfills. And they sometimes resemble or represent the last land available in an area. Suburbs or even urban areas have grown out around landfills. They're some of the last large parcels of land available. I think also that landfill redevelopment can improve the care of landfills post-closure. Most regulations require a quarterly site visit to see if the cover is doing all right and so forth. Well, if you have a shopping center on a landfill, people are there every day. And if a hole develops in the cover, the management of the shopping center will hear about that pretty quick and will take responsive action to deal with those kind of issues. So I think landfill redevelopment can be smart growth. There are three categories of challenges that I want to go over briefly this morning before turning it over to Eric and to Mark for some case studies. The three categories are, I want to talk a little bit about legal issues because a lot of potential landfill redevelopers are struck first by the legal issues involved in these projects. Then we want to talk about some technical issues, primarily gas mitigation and foundation settlement. And I want to talk a little bit about costs, although costs kind of fall into two buckets. On the one hand, it does cost more to redevelop a landfill. There are some features that you have to build in that you wouldn't have to build in to a greenfield development. But on the other hand, you're buying the land typically for much less than you would be buying a greenfield nearby. And so you have to consider costs in that kind of total context. With respect to the legal issues, we have a defense to the federal Superfund liability that can otherwise attach to site developers, site owners, a defense that is relatively new and has been successfully used. The bona fide prospective purchaser defense requires a few things to be present for the landowner to be able to use this defense. For one, the disposal of the site had to have been before he took or she took title to the facility. They had to have undertaken all appropriate inquiries into the prior uses of the site, and that would be, for example, to find out that it had been used as a landfill. You've got to comply with the institutional controls and essentially the regulations that apply to a closed landfill, which varies obviously from location to location and from landfill to landfill. You also have to exercise appropriate care with respect to the things you know about the site. And what appropriate care can mean stopping things like drums that are leaking on the surface of the ground and that kind of thing. But really, to cut to the chase, what you really want as a BFPP is not to make the contamination worse at a site. The idea is that you don't move things from contaminated areas to uncontaminated areas. Don't let things leak into wetlands and so forth. Don't make the contamination worse. First, in the technical issues that we all have to address, in many landfills anyway, are foundation and settlement issues. Depending on what the nature of the waste is, how fresh it is, how much organic material it has in it, you're going to see decomposition and settlement over time. If the waste was all placed there years and years ago, perhaps less settlement. If it's relatively fresh, probably more settlement. And in general, it's not easy to use models to predict these things. It's better to go out and measure them in the old engineering way. We found that measuring actual settlement is the way to do this. And there are easy ways to do that relatively quickly that can get your arms around those parameters. We normally at least consider putting heavier structures on deep pile foundations. And that can set up a sort of a challenge when the building is not moving, but the ground around it is. And so you've got the potential for a fall out of a building if you're not paying attention, watching that first step. And you've also got the potential for utilities and the like to shear off when the building falls down that way. And you've got to plan ahead for those kind of issues. In addition to that kind of hard edge settlement, there's a soft edge settlement which can interfere with things like drainage. At Virginia Tech, they taught us that water wants to flow downhill. That's fine, unless the land has subsided and there's now a pond where there used to be a grade to promote runoff. There are proven techniques for addressing these issues, everything from shallow footings and slabs to the deep kinds of foundations I mentioned a minute ago with driven piles or driven piles, grade beams, structural slabs, those kind of things. We also can put in reinforcement, plastic grid reinforcement to minimize differential settlement at the surface anyway. And we can improve the ground using either surcharge, which is a time-honored approach to loading up the site so that it goes ahead and accelerates settlement, or deep dynamic compaction, which we'll talk about in just a second. And I'll put it at the bottom of the list. It can be suitable for some sites, removing the waste and replacing it with structural fill, which can be a pretty expensive operation, but certainly can be appropriate for some kinds of site developments. One of the questions that we often hear from regulators the first time we talk about driving piles through a landfill is, gee, won't this create a direct pathway or a conduit for contamination to move further into the earth? And the short answer, there are answers to this. There's some science and research out there that we bring to their attention. But in terms of direct displacement, that really is a very low probability. There's not much of a footprint that the pile has that can carry waste deeper. And in terms of a conduit, what you have when you drive a pile through a clay liner, for example, is you make the clay actually denser right next to the piling. And what that means is there's actually less likelihood of leakage right around that more dense clay, right around the edge of the pile. And if we use timber piles, you could have the potential for wicking, but that could draw some contamination deeper. I mentioned earlier that one of the concerns we have is about planning for settlement so that utilities don't shear off. Here are a couple of details of how that is done. And of course, we also want to protect piping and so forth that's beneath the slab of our building. We often hang those on hangers to keep it from moving if the earth wants to slide down, if it wants to settle below it, we want to plan for that settlement and make sure that our utilities stay in place. A related concern has to do with bringing subsurface utilities onto a landfill site. The The trench that's constructed for utilities can serve as a preferential flow path for migrating landfill gas. And so we often construct bentonite check dams essentially in those trenches to make sure gas can't move off-site. Deep dynamic compaction is essentially a brute force method. It's like taking a large hammer and pounding the surface of the landfill. If you do that enough, you can actually have effects down 25, 30 feet deep in a fresh municipal solid waste landfill. It's a good technique for near surface stabilization. It works best on flat areas. Doing it on side slopes can be challenging. Moving now to landfill gas, which is another one of these key technical considerations for landfill redevelopment. If you bury anything organic, and if the organic material is cut off from the air, from the oxygen, anaerobic microbes will take over and they will decompose that organic material and create decomposition gas. And I often hear it said that methane, which is a component of decomposition gas, it's about 50% methane and 50% carbon dioxide. Many people focus on the fact that methane is lighter than air, which is true enough. But landfill gas, decomposition gas, the combination of methane and carbon dioxide has about the same density as air. What makes this a problem or a challenge is that if you have an enclosed space that's collecting this decomposition gas, if you have oxygen in that enclosed space and a source of ignition, you can have an explosion. And explosions happen everywhere, every year, somewhere in the world. There are decomposition gas explosions, and people have been hurt from those explosions. When gas is produced very rapidly, and it has not much room to spread out in the subsurface, you can see pretty substantial pressures build up. And those pressures can drive gas into structures. And where you have that situation, a lot of gas being produced and a lot of pressure being produced, you've got a different kind of a challenge than if you have simply diffusion or kind of concentration-based migration. If you have sustained pressure in the subsurface, you have a different challenge. In addition to pressure, we also care about how much methane is in that decomposition gas. Obviously, that matters. The regulations focus on gas quality, for example. There are lots of proven approaches to solving the landfill gas problem, challenge at sites. I first want to put a caveat out there. There's a whole separate webinar that we should have on the subject of trace contaminants, trace chlorinated solvents that might move up from contaminated groundwater into structures. Some of the technologies are similar, but that's a completely different subject. What we're talking about here today is landfill gas mitigation. And we normally have several, as I say, several techniques available to us. We can passively vent that landfill gas from around our building. We can put in membrane barriers, or we can put in a combination of passive venting and membrane barriers. And if we have enough gas being produced, we can supplement those techniques with an active subsurface subslab ventilation system. In our experience, a lot of our landfill redevelopers take a belt and suspenders approach to mitigating landfill gas. They will put in both a barrier and a venting system and active ventilation, even if the situation wouldn't technically require it, and all of that is fine. It is a little bit of a challenge operating blowers around the clock. Some of our more recent systems have got pretty sophisticated controls that only turn on the blowers when they're needed, and when there's methane there to be swept out of the subslab. Alarms are very popular. People like to put sensors and alarms in buildings as one more layer of protection. They can provide peace of mind, or as I say on this slide, or not. False alarms don't provide peace of mind. What they tend to promote is disconnecting the alarm in our experience. But there are ways to minimize, reduce the potential for false alarms, and thus increase peace of mind. Just a few pictures here of what these venting systems look like. This is actually a single family home in the upper left-hand corner with a venting system going underneath its slab on grade. That's what the yellow materials are. The lower set of pictures are sheet membranes put over areas that have got grade beams separating them. And one consideration is to make sure that they're able to breathe, so you don't have isolated areas, eggshell carton, if you will. It's isolated and can't breathe. Again, passive systems in that application. Sheet membranes are pretty good. We also have had good experience with spray applied asphaltic membranes. This is somebody putting down a liquid boot from Setco. It basically is built in the field, fabricated in the field, and subject to separate construction quality assurance. I'd like to speak very briefly about construction worker health and safety issues. Some of these old landfills date to a time when hazardous waste regulations weren't in place. There can be surprises. There could be industrial waste in some older landfills. And it's just something to be prepared for. Preparation is the best part of good luck, I think. And you'll want to have a written health and safety plan for the people that are doing work invading the old landfill. You want to do some air monitoring to make sure they're protected and have some contingency plans in place in case they bump into something that you weren't expecting to bump into. I want to talk just a little bit about the incremental cost of developing on top of a landfill. Doing things like structural slabs and deep pile foundations can add expense to the construction. Again, you've offset that in theory by the lower purchase price for the land. Deep dynamic compaction's got a cost associated with it. Putting in gas protection systems can add a few dollars a square foot for the first floor square foot area. And if you add ventilation to it, that can add some additional expense. And then just in general, you put in a little more money for things like maintaining parking areas and the like, because instead of having to repave those every 10 years, for example, you might be repaving them every 7 or whatever the case may be. We've got a bunch of project examples, and we're going to go through the first 2 of these with you today. A produce market up in Philadelphia, Pennsylvania, that my colleague Eric Peterson will be talking about, and then a solar development on top of a landfill in Beloit, Wisconsin, which my colleague Mark Huber will be talking about. But the slide deck has got a couple other case studies in it, and if you request a copy of the slides, you'll get these as kind of bonus content. I don't think we'll have time today to go through these, but who knows, we may put up a picture or 2 to help illustrate. With that, I'm going to stop talking. I've done my introduction and turn this over to my colleague, Eric Peterson.
Thank you, Mike. I'd like to point out that I've worked on a variety of projects for landfill development, including parks, golf courses, dog pounds, prisons, hotels, office buildings, and residential. This particular one is for a produce market. It's interesting that it's a very large building, and the challenges that we had were pretty reflect many of the ones that Mike pointed out. So it's should be a good case study to go through. In fact, Mike and I, our first project, my first brownfields project with him was in 1986 for a Marriott hotel being built near Chicago O'Hare Airport. We have a map here where the facility was located, indicated as the main facility on the Schuylkill River. I think I hit the down button too many times, so it's advancing quickly. This aerial view gives you an indication that it's in a rather industrial area. There's some fuel tank storage, tank farms nearby, and across the river to the right beyond the slide, there was a Sunoco oil refinery. The location of the facility, we're talking about landfills. I call this more of a junkyard / construction debris landfill. This is pre-development photograph of the area. And the site is about 50 acres, half of which was landfill material, 15 to 25 feet deep. The previous consultant did a series of test pits and monitoring probes, as you typically would do. They found methane in the 50% range, slight pressure. I should point out that no matter how old or how little organic material you have, the microbes are still going to produce it at, in the 50% range. So we worked at sites in Alexandria from the old canal that was filled 80, 90 years ago, but there's still 50% methane being produced, just in very, very small quantities, which then results in low pressures and certainly factors into the hazard level that can develop. For this site, we found very little pressure and weren't anticipating a whole lot of gas generation. We modeled that about 80 CFM would come from the entire site. So although there was a recommendation by the previous consultant to perhaps install vertical extraction wells to remove the gas, that's a challenge for a couple of reasons. One is with a building this size, over 500,000 square feet, it'd be difficult for vertical wells to influence beneath the building, and also you introduce the possibility of air permitting if you're going to extract gas in that manner. As shown here is sort of an architectural rendering. There's a large building with truck loading docks on all four sides. And in this next slide, we discuss the, sorry about that, the type of construction it was. Originally, it was going to be supported on timber piles. And as Mike mentioned, that on a pile foundation, you're supporting a structural slab, which is independent of the soil beneath. So the soils can settle with the waste below it, independent of the first floor. And creates a challenge not only for the utilities that need to be hung from the underside to keep them in place, but also if you're using sheet membrane, for example, that needs to be attached at the edges, and sort of ends up draping over the utilities. And you also have the added challenge of each pile has a pile cap or cluster of piles to support the slab and also the columns above it. So each pile cap creates a sort of a detour for utilities that are running across the building. It's also a point of attachment for a sheet membrane. So normally, if we have a deep foundation and structural slab, a spray-on type membrane has a lot of advantages. However, at this site, the value engineering during the design process determined that controlled modulus columns, which are sort of a combined auger grout injection process to create, modify the soil, sort of like concrete columns that are installed very close on center. At this particular site, we had, as it says here, approximately 10,000 columns, and above that, a 3-foot layer of engineering fill that allowed for a slab-on-grade type construction, which simplified matters for the methane remediation. The construction project was about a 2-year process. Here's a couple of pictures pre-development on the top left, right, and bottom right. And then in the bottom left, you can see some of the earlier phases of construction. In regards to the methane mitigation, we had from top to bottom, or bottom to top, let's say, a gravel vent layer, the membrane, and then the concrete slab with vent piping in the gravel vent layer. noted here that originally, when we were talking about a deep foundation, the spray-on membrane was proposed. When they switched to a shallow foundation, actually the membrane supplier had determined he could use sheet membrane more economically. So that's what was installed. As I'll point out in a minute, that sheet membranes require a boot for every penetration, or as a spray-on, you just, as you're spraying, you're creating the boot with the spray itself. And this large building had many penetrations with conduits and utilities, plumbing and whatnot, each of which had to be booted. This, the way we structured the remediation, I'll show a few slides in a minute. We had vent piping that crisscrossed the building. Every other run of vents were connected to a manifold that in certain places would go up to the rooftop. We had a series of 4 blowers on the roof to apply an active vacuum beneath the slab. And then every other cross vent would go to a different manifold that had a series of vents along the loading dock that were fresh air inlets, so that in an active mode, you would be flushing clean air through, pulling it through the subslab gravel layer to remove any accumulated methane. We also had a monitoring system inside the building, 6 sensors. That's a very simplistic system for a building this large, but the type of building it was and the very limited amount of small spaces on the first floor made it a reasonable approach, and it also keeps things simple for the owner. I mentioned at the beginning, I've worked on prisons, probably 5 or 6 prisons, where you have a series of small, confined, locked spaces, which are, of course, a higher risk for methane infiltration and accumulation. So there we have much more sophisticated methane monitoring systems. Lastly, we have subslab monitoring probes in certain zones of this building. And the purpose of these is, one, to see what kind of methane is beneath the slab, but we expect some methane beneath there because it's below your control system, but it also provides a means of checking your active extraction, that your vacuum distribution is good beneath the slab. You'll see in these pictures different sequences of construction. On the top left is sort of the beginning of the gravel layer. You see the white pipe along the left side is one of the manifolds I spoke of. The gray kind of a ribbon-looking thing in the lower left of the upper left picture is a geovent type venting device that ran across the building in the short way. And then the next picture is the completed gravel layer, with the dark material being the protective geotextile and the shiny material being the membrane, and a more full picture of the membrane deployments in the lower left. I mentioned that we had a series of 4 blowers on the roof. We ended up activating these, running them full time. Here's one of the 4 blowers. You can see the refinery I mentioned in the background. Besides this main structure, the 500,000 square foot structure, we had a guardhouse and a recycling building. At the guardhouse, we had a situation where the design called for the membrane passive venting through the roof. It was probably about a 600 square foot building. But it had a lot of telecommunication cable conduits coming in through a small communications closet and causing odors. And there was a lot of spare, well, not a lot, 3 large spare conduits that gas from the subsurface was coming in and causing an odor. So we ended up modifying that design. So instead of your belt and suspenders, we added an elastic waistband by having an interior ventilation fan that was sensor activated in this telecommunications closet. We also made the passive vent active by putting a radon style fan on the vent piping through the roof. Even with all these things in place, membrane, vacuum applied through the vent layer, you still have one critical pathway that you need to control, and that is through penetrations of conduits and utilities that come up from beneath the slab into the building. Here, this gives you an example. At this site, there was had to have been several hundred conduit penetrations coming up through the slab. The picture on the left is just one bundle of conduits in one small section of the building. After the building was open, before occupancy, we were testing the sensors, and we had an alarm going off that we determined was coming up from the conduit bank near the elevator shaft. You can see on the right, these are conduit seals. So every conduit, because they're not gas tight and methane can get into them as they run beneath the building, and unless you install a seal, which is like an epoxy between the conductors and the conduit to block the methane, you can have a leak. Well, the contractor forgot to install that epoxy. In the second from the right seal, you can see there's a little bit of drippage from him coming in after the fact. So put in the epoxy, which stopped the alarm, and we haven't had any alarms since. So just a note of caution that quality control and little things like conduit seals are something you really need to keep track of and make sure are installed properly. This last slide is just a picture of the finished product. Once it comes up, you can see in the upper left, that's the exterior of the building, and the inside of the building is in the lower right-hand side, which you can see is quite a large open area with lots of produce vendor stalls and forklifts running all over the place. And that's the end of my case study, and I'm going to hand it over to Mark to speak about solar development on landfills.
Hey, Eric and Mark, if I could get a word in edgewise, we do have a question that's been chatted into us, or question. Somebody used the Q&A to ask a question. How do you interpret 75% methane concentrations in soils, since decomposition gas is roughly 50-50 methane and carbon dioxide? Eric, I have an answer, but I'd be more interested in yours, perhaps.
Well, we have seen this, and we've seen 90-95% methane, and under certain conditions, the CO2 is much more soluble in water than methane is. So if the gas is passing through saturated soils, that sometimes is the mechanism where the methane becomes enriched by virtue of the CO2 being depleted in the gas mixture. We've also seen or postulated under high pressure migration, we've seen a couple PSI of driving force behind methane leaving an active deep landfill. And I think the porous media of the soil can act like a gas chromatograph and separate the gases by density. But I think the primary issue here is the solubility of CO2 in water.
Okay, thank you for that.
The one other thing is, if there is some other, depending on the gas instrument you're using, if there's some other hydrocarbons in the or VOCs, they can interfere and cause a false high methane reading. So you might need to do a lab sample.
I'm smiling because Mickey McCourt just concurred with your explanation.
Okay.
Mr. Huber.
Well said. Thank you, Mike. Great presentation, Eric. I still marvel at finding that methane leak in a building of that size. That's some great detective work. So switching gears here and talking about a case study about solar on a landfill in a town called Beloit, Wisconsin, just south of Madison. project site is owned by Alliant Energy. When this project came up, I got pretty excited. I have a short 30-year career. About half of that has been working on brownfield projects and the other half on solid waste projects. So whenever I get a chance to work on both of them at the same time, I get pretty excited. And then a while back, I found this quote by Thomas Edison, almost 100 years ago. He's putting a big bet on solar energy. I think he'd be pretty surprised by what's going on these days with the amount of solar energy going in on a daily basis. But I really agree with this quote. I think it's the simplest form of getting energy. And when I can work on a brownfield, on a landfill, and then throw solar in there, I've pretty much hit engineering nirvana. So one of my all-time favorite projects so far. Here's the site, really a kind of a neat site. We have on the far right, the coal-fired plant that has since been demolished. Over in the background, we have a fairly new natural gas-fired power plant. In the middle here, we have what was a very large coal pile at one time. All that coal was shipped off site, and we were left with just a little bit of coal mixed in with dirt here. And then when the boilers were running under coal, the ash material that was created from burning the coal was mixed with water to be conveyed out to several ponds over here. The ash material would settle to the bottom, and the clean water would go off the top and into the Rock River. Over time, the ash would accumulate in the ponds, and it would be excavated, dredged out of these ponds, and then placed into the landfill. The coal-fired plant ran for almost 50 years, was eventually converted for a short period of time in 2000 to a natural gas-fired plant. And then starting in around 2012 through 2016, the plant was decommissioned, the ponds were closed, and solar was installed on the landfill. Anytime we're looking at redevelopment on a landfill, there's really two basic questions we need to ask. How does the landfill affect the development? And really the flip side of that, how does the development and the construction that goes with it interact with the landfill? On this site, we started to answer those questions by first looking at the feasibility of solar on the site. The instrument on the right-hand photo is a solar pathfinder. You just take that out to the site and walk around with it and measure the angle of the sun and determine how much energy you'll get. You're basically looking to see if there's heavy shading that would obscure the panels and reduce their effectiveness. While we were walking the site on a very cold day here in Wisconsin, doing the solar pathfinder work, we observed a lot of condensate coming off that natural gas-fired plant, and we were a little concerned that that might cause some shading. So we did a quick little wind study. As you can see over here, the prevailing winds out of the west were blowing the condensate away from the solar facility and would not then cause a major concern in terms of reduced electricity production. So once that it was determined that solar was probably a good thing to try at this site, our client Alliant went off to recruit a solar developer and asked us to start working on a plan to close out the coal yard, the ponds, and the landfill. So our primary mission was to take the coal and dirt that was left over from the coal yard, as well as residual materials in the ponds, and consolidate them with part of a closed landfill and then what became a new landfill. The trick here was just the volumes of those materials are a little bit uncertain, so we had to have some flexibility in our grading plan so that cover could go up or down based on the final volumes of material moved during construction. At the same time, we needed to make sure that the grades of the landfill were ready for solar, so we needed to make sure those grades were between 2 and 10%. We don't want anything too flat or too steep for solar. And we weren't looking to put solar on the steeper 4-to-1 slopes that we needed to make a couple of transitions. The final cover system for the landfill, once all the materials were consolidated, consisted of these layers. The most important, or sort of the queen bee of this, is a laminated GCL, or geosynthetic clay liner. That's some clay sandwiched by 2 geosynthetics, and then for extra protection, this one has a membrane applied to that GCL. I have just a series of slides here showing the GCL going down on top of the landfill, and then just a protective geosynthetic going on top of that. And then on the steeper slopes, we had them roll out some geocomposite and some drainage layer that we'll take a look at in just a minute. And then finally, we put on a fairly thick 24-inch general fill. That's often called a rooting zone. It allows the roots on the cover above a place to go so that they don't penetrate the cap over time. It's just a cross section of the closed landfill. The main point here is that the stability of the landfill cover was really important. We wanted to make sure that we didn't lose the cap itself down into the pond below, and we certainly didn't want to lose any of the solar panels that were about to be installed on it. So that drainage layer was installed on the steeper 4-to-1 slope so that when the rainwater hits the cap, it has a place to go laterally instead of vertically. The function of the cap is really there to keep water out of the materials below so that they can't mix with the rainwater can't mix with the waste and then cause a groundwater problem down the road. So this drainage system helps manage that storm water that does hit the surface. One of the next big hurdles for this project was making sure that the loads of the construction of the solar system wouldn't impact that GCL layer. And what we found out during the design is that the panels themselves have very little weight. And in fact, the concrete grade beam that was installed to hold the panels, mount the panels on, was actually serving more to make sure that the wind loads didn't topple over the panels than it was there to really protect the cap below. In addition to the solar panels, there's some other equipment that got mounted on the grade beams. We're depicting here, one of the pieces of equipment is called an inverter. The solar panels collect energy in direct current, and that has to be converted to alternating current so that it can be used on the grid and brew our coffee and reheat our meals in our microwaves. It's just in addition to the grade beam that went on the cap, we did have a few places where we had to have some underground utilities. And the main goal there was to make sure that those conduit runs were kept shallow enough that they didn't interact with that GCL membrane. Just a series of slides here showing the grade beam going in. This is the shallow cut that we did into the cap. Really barely even dented the topsoil layer here. And then put in just a little bit of gravel to support the grade beam. Put in the grade beam itself. One of the innovations the contractor came up with on this project was to pour the grade beams offsite in their yard and then bring them to the site on a large flatbed trailer and then use a small crane to put them in place. That was a good way to minimize the loads and traffic on the cap while the solar facility was being installed. And then the last shot here is just those conduits. We're just measuring down from the top of the cap to make sure that we don't get too deep and interfere with the GCL below. And there's the completed solar panels on top of those grade beams. Maybe not quite as interesting as the solar panels themselves, but site access over the top of a cap is an important consideration. And we had to do some geotechnical analysis to make sure that the vehicles that would need to go on the cap to help maintain the solar system would not disrupt the cap, particularly that GCL layer. So we did some conversations with the solar developer and the local emergency departments and found out what size vehicles would be up there. Turned out they were pretty light, and the road that we needed to put in didn't need to be too thick to support those vehicles. So we were able to have a fairly shallow road section. Here's just the gravel being put out. with some wide tracked vehicles so that it doesn't disrupt that GCL, and then a compactor pushing it down into the ground. And there's the final road. Stormwater management is always an important consideration on any development. In this case, we were able to protect the cap with some good sloping away from the high to low points. We had a pond that was actually a former processed water pond. The easiest way to get that pond closed out was actually to turn it back into a pond after we got rid of all the contaminated material. And in this case, we were able to use a conduit run. We're able to locate that directly under a stormwater culvert, allowing us to kind of keep everything shallow and use the road that went over the top to get to the cap kind of as a dual purpose. Erosion control is really important before the vegetation on the cap is established. And one of the things that we used here was something called wattles, serve the same purpose as silt fence, just trying to slow the sediment transport down. The advantage of wattles is that we just need to stake them they just need a little bit of staking into the ground, so we didn't get anywhere near the GCL layer down below. We also used erosion matting where water was being concentrated to keep that in place, and some check dams in the swales as well. Here's the completed project with the solar panels on top of the cap, and then the large pond down here. And again, I'll just point out that that pond is serving many functions, one of which is to help manage stormwater and runoff from the cap, but also was really the easiest way to close out that pond after the material was excavated and put into the landfill under those solar panels. We didn't have to come back in and replace the fill that was taken out with a bunch of clean fill. We were able to just create a pond, which makes a nice feature for the site. So at the beginning of this case study, we were looking at two questions. Does the landfill affect the development? And we're able to firmly answer that question, no. The landfill and development get along quite well. We achieved a nice symbiotic relationship that we were looking for. At the end of the day, we ended up with 7,700 panels on the cap, which generate about 2.3 megawatts of electricity, which is, depending on how you calculate it, about 400, enough to power about 400 Wisconsin homes. And at the time, this was the first utility scale solar project on a closed landfill in Wisconsin. Certainly, we hope it's not the last. Couple of advantages of putting solar on landfills is that, particularly in the case of coal combustion residue or CCR sites, they're very close to grid infrastructure or the interconnect. That's where the power is taken from the panels and put into the grid. They have acres of open space. In this case, that cap was about 14 acres. And it's really smart land use. There aren't a lot of other things you can do in some of these more rural electric utility sites, but solar is a great option. And if you can put solar on a cap, certainly here in the upper Midwest, that is good for the farmers because they definitely like to see their farmland preserved. Just to wrap up, there has been a lot of interest in the more recent years of doing solar on municipal solid waste landfills. There are some strong financial incentives to do solar in general, and those also apply to solar on landfills. What we've seen so far is that the older closed landfills, sometimes affectionately known as the town dump, with their flatter surfaces, are really amenable to solar. The kind of more modern landfills with their 4-to-1 side slopes are a little trickier, but we are starting to see some new products come online that look very interesting. Those include some of the artificial turf. I know that some of the vendors are starting to embed solar panels right into that turf, so you can close out your landfill with the geomembrane, a surface turf, and synthetic turf, and then solar panels all at the same time, which can greatly reduce the cost of your cap and turn it into a money generator. Also, we're seeing a lot of the older landfill gas to energy, particularly the gas to electricity systems starting to run out of their contracts or just run out of their useful life. Because those facilities already had an interconnect, a good connection to the grid, those landfills make a good option for solar because you can use that same interconnect and infrastructure that's put in place. And with the ever decreasing cost of solar panels, the option to put solar on landfills gets more attractive every day. So that's what we had for the presentation. I'll turn it back over to Mike for any remaining questions and answers.
We do have one question. Has to do with, have we worked on any solar development projects at closed MSW landfills that have active gas collection systems? I guess, Mark, you just alluded to that. I know that Eric has, because New Jersey is full of landfills with active recovery systems and solar on top.
Yeah, we're definitely involved in a few. We're operating a gas system with 2 flares at a large landfill about 8 miles from my office in Mount Holly, waste management facility. I was only marginally involved in the solar development project, just as a certifying engineer on the cost profile for getting a loan through the state that was, subsidizing solar development when that was installed. But there's, definitely a number of projects where we're engaged with active gas extraction and solar panels in place.
I would say that, the modern landfills, to quote Mark Huber, they have a lot more controls, leachate, gas collection systems, and so forth, all of which have to be coordinated with redevelopment. But it's been very interesting doing that for some pretty innovative land uses. I hear, Mark's 2 questions that he asked at the beginning and the end of his presentation reminded me that my colleague Brad Johnson and I a few years ago had a session on the landfill whisperer. I hear you help people with their landfill problems. And the landfill whisperer answer is actually, no, I help landfills with their people problems. It's just a matter of your perspective. If anyone has any questions, feel free to use the Q&A function and send them on in. We'll do our best to get you an answer. I mentioned earlier that this phenomenon began, at least in my experience, in Southern California, but it's expanded to just about every part of the country. We've done these projects, I think, literally just about everywhere. There's some absolutely amazing projects that have been done in South Florida, for example, here just in the last few years that my colleagues down in our Miami and Miami offices have been working on down there. In the Southeast and Georgia, there are at least a couple that we've been working on. There are quite a few here in the Washington metropolitan area and all up and down the mid-Atlantic. And then as Mark has illustrated, all over the Midwest. It's not limited to just places where real estate prices are really high. It helps if real estate prices are really high, but landfill redevelopment can be smart growth just about anywhere. And we do have scores of examples that we can share with folks. We have had to share with skeptical fire marshals and regulators who are worried about how these challenges have actually been overcome. Before I finish up with my summary slide, we did have a question just sent in. Have we worked on any dual use projects on closed landfills? A dog park underneath the solar panels. I'm not sure a dog park under solar panels is coming to mind. Any of you guys have a dual use landfill redevelopment?
As in solar plus development?
Yeah, for example, I mean, that's the example that Maurice is asking about.
It's a very interesting idea, but I can't say that I've come across it here in the Midwest.
We're working on one now that's not a passive recreation site, but an intense active recreation site that will have solar on it. I guess a challenge with passive recreation, it's a little hard to walk around the solar panels, but I guess the Rio Salado area, I'm trying to remember now, down in in Phoenix, Arizona, seems like they were incorporating a whole variety of recreation land uses with some solar, as I recall down there. That might be one example. You need to have, I guess, a passive recreation thing that you're doing that's compatible with solar panels, right?
Right. Yeah, the only other thing I think of is, development for office parks and whatnot that may employ solar panels on the roof or over their parking areas. But I'm not familiar with one yet.
Well, again, the wrap up here is we're approaching the end of our hour, and I'm here as long as anybody wants me to be here. This has been done in scores of landfills all across North America, and it's been done successfully. There are technical challenges, but there are also proven solutions to those technical challenges that are site specific. But again, we've been able to, and a lot of developers have been able to do these projects successfully using some of these proven solutions. And I think the fact that the closed landfills are often well served by existing services, utilities, interconnects in the case of solar and transportation corridors and the like, I think that these projects are almost the poster child for what I call smart growth. I so appreciate you all joining us this afternoon. This is one of my favorite topics to talk about. I get a lot of personal and professional satisfaction out of the work that we do here on these landfill redevelopment projects in particular. And so thank you for indulging me in one of my passions. I very much appreciate it. Thank you.